The separation techniques according to crystallizability are TREF, temperature rising elution fractionation; DC, dynamic crystallization; CEF, crystallization elution fractionation; and CRYSTAF, crystallization analysis fractionation. TREF, DC, and CEF can all be performed by one instrument in a column packed with an inert support. CRYSTAF, however, has to be performed in a separate equipment because it uses crystallization vessels. TREF, temperature rising elution fractionation. TREF was developed in the late 1970s and has been the most extended technique for analyzing CCD in the industry for many years. In the early days, analyzing one sample could take up to a week. Today, it can be performed in under 2 hours. We will use the simulated analysis of a 3-monodisperse polyethylene copolymer blend with different comonomer content to understand the principles of the crystallization techniques. In TREF, the sample is dissolved and injected into the center of the column at high temperature. As the temperature gradually goes down during a slow cooling ramp, crystal aggregates of different composition deposit. In the case of polyethylene, the homopolymer without branches crystallizes first, followed by the fraction with more branch density per 1,000 carbons. However, at this stage, there is no physical separation of these fractions. To complete the separation, a second temperature cycle is necessary to elute the fractions of different composition. Temperature is increased to dissolve the fractions of higher crystallinity while monitoring the concentration, achieving the separation of the 3 components in this case. DC, dynamic crystallization. DC is a new approach to analyzing the SCBD during the crystallization process, similar to CRYSTAF using a column instead of a vessel. The polymer fractions are physically separated along the column. In addition, by segregating the most crystalline fractions first as the temperature goes down, minimizes nucleation, and thus the co-crystallization of subsequent less crystalline fractions. In DC, the sample is loaded to the column's head, and once the crystallization ramp begins, a small flow passes through the column. The polymer fractions are deposited on the support when reaching their crystallization temperature, achieving a physical separation along the column's length. The crystalline homopolymer fraction remains at the head of the column, and the most amorphous fraction flows toward the end of the column. Once the crystallization cycle is completed, the flow stops and temperature is increased to dissolve in situ all components still deposited inside the column. After a few minutes at high temperature, the flow resumes to elute the components from their positions within the column. The elution volumes are related to the crystallization temperatures and thus to the number of branches per 1,000 carbons. The separation by DC is equivalent to that obtained by CRYSTAF, and the larger the column volume, the higher the resolution. CEF, crystallization elution fractionation. CEF was developed in 2006 as an extension of the TREF crystallization technique in a process that combines the separation obtained in the crystallization cycle DC with that obtained in the dissolution step of TREF. CEF has become the most popular crystallization technique in the industry these days. CEF also gives name to an instrument capable of performing TREF, DC, CEF, and the chromatographic TGIC technique, all in the same equipment. In CEF, the sample is loaded to the column's head, and the crystallization proceeds as in DC with a crystallization flow. The polymer fractions are deposited on the support when reaching their crystallization temperature, achieving a physical separation along the column's length. Once the crystallization cycle is completed, the temperature-rising elution cycle begins with the elution flow that further separates the components when reaching their dissolution temperature. The polymer components are eluted with an extended Treff separation from the DC cycle. With standard short columns, the additional separation by DC is relatively small. The larger the column's volume, the higher the contribution of the DC separation. Designed and developed by Polymer Car, your trusted partner with over 30 years of experience in advanced polyolefin characterization instrumentation and world-class analytical services.